Today we will discuss about two topics, that is intermodal dispersion and polarization mode dispersion. First we will discuss about intermodal dispersion. We know that dispersion is classified into two, intramodal dispersion and intermodal dispersion. Intramodal dispersion we have discussed in the previous class. Today we will go to the details of intermodal dispersion. See, intermodal dispersion is also called modal dispersion and it occurs only in multimode fibers. We know that multimode fibers can be implemented as step indexed fiber or graded index fiber. So, intermodal dispersion occurs in multimode step indexed as well as multimode graded index fiber, but its dispersion effect is maximum in the case of multimode step indexed fiber. So, the multimode step index fiber shows large amount of intermodal dispersion and that produces a high pulse broadening. We know that the effect of dispersion is that it will produce pulse broadening at the output. So, in multimode fibers, we know that the input light pulse is made up of a number of modes. So, all these modes, different modes, travel through the optical fiber with different speed, and in different, that will be in different directions, and so the distance traveled by each mode is different. That will gives rise to a propagation delay between different modes. So the time taken by each mode to cover the same distance is different, and this causes at the receiver end, this causes the pulse broadening, and the pulse broadening increases with the increase in the distance travelled by the light pulse through the optical fiber, and figure shows the intermodal dispersion, and here we are explaining the intermodal dispersion with the help of a diagram that uses the ray theory of light, and here at the input side we are giving the modes excited, that is at the same time, and these modes are traveling through the optical fiber, and optical fiber is shown here, and you can see that each ray is traveling at a different path, and this each ray shows different modes, and we are explaining this with the help of ray diagram, not with the help of wave diagram. Okay, so you can see that different modes will travel with travel at a different path, and at the receiver end the pulses will received at a different, or rays will received at different times. So this results into pulse broadening, and this figure shows the distance travelled by each mode over the same time span, and you can see that at the receiver end pulse received will be broadened. So the intermodal dispersion or modal dispersion is the main source of dispersion in the multimode fibers, and the propagation delay of various modes in multimode step indexed fiber is high, and this can be reduced by the use of multimode graded index fiber, and you know that in the case of graded index fiber the grading of refractive index is there inside the core, and that will give a parabolic refractive index profile, and this parabolic refractive index profile will reduce the distance travelled by each mode, and this in turn reduces the propagation delay, and we have discussed about the propagation of light through the graded index fiber in the first class. So I am not going into the details of that. So we can say that the pulse broadening effect can be reduced to some extent by the use of multimode graded index fiber instead of step index fiber. So a single mode fiber propagates only the fundamental mode, and the modal dispersion does not exist in single mode fibers. You can see that in the case of intermodal dispersion it will result due to the difference in the velocity of different modes when it is propagating through the fiber, but you know that in the case of single mode there is only one mode, so there will be no intermodal dispersion. So single mode fiber propagate only the fundamental mode, and modal dispersion does not exist in the case of single mode fiber, and therefore the single mode fibers exhibit the lowest amount of total dispersion. So the single mode fibers also exhibit the highest possible bandwidth, so they are preferred for long haul communication. So for long haul communication, single mode fibers are preferred because when we are calculating the total dispersion in the case of single mode fiber, it will exhibit a lesser amount of dispersion comparing to that of the multi-mode fibers, because in this case of single mode fiber there are no intermodal dispersion. That is why it is preferred over long haul communication. And in one university question it is asked that how single mode fibers are used for how can you say that single mode fibers can be used for long haul communication. So you can write this as its answer. And the next topic is polarization mode dispersion. And before discussing to the details of polarization mode dispersion, you should know about what is fiber birefringence. Actually it is a basic topic, fiber birefringence. And we know that in the case of multimode fibers, modes propagate with different phase velocities in an optical fiber, and the difference between their effective refractive indices is called fiber refringence. That means the difference in the refractive indices of each mode is called fiber birefringence, and it is given by the equation fiber birefringence, that is Bf equal to Nx minus Ny, where Nx and Ny are effective refractive indices of each mode. Here we are assuming that X and Y are the modes, so we will get the equation Bf equal to Nx minus Ny. And next we will go to the topic polarization mode dispersion. So we have discussed that dispersion is of two types, intermodal dispersion and intramodal dispersion. That is the basic type of dispersion. Apart from those two dispersions, there is another source of pulse broadening. You know that dispersion causes pulse broadening, and the main cause of pulse broadening is intermodal dispersion and intramodal dispersion. And apart from those reasons, there is another source of pulse broadening, and that is by the fiber birefringence in the polarization states of an optical signal. Usually we know that what do you mean by polarization? Polarization means that it represents the electric field orientation, right? And you know that polarization refers to the electric field orientation of the light signals, and if the polarization state varies with the distance travelled by the light through the fiber, and the fiber is birefringent, it causes each polarization mode to travel at a slightly different velocity. You can see it from the figure. See here in the first diagram, x and y axis are marked and z direction is the direction of propagation. Actually it is not marked in that diagram, and you can see that one sine wave is propagating in the yz plane and other sine wave is propagating in the xz plane, and these two represents the electric field plane and magnetic field plane, and you can see that it is propagating in that manner. And suppose if an input pulse in the second figure, if the input pulse is given to an optical fiber, see in the optical fiber cable sometimes some factors will result into the propagation of the pulse through some in a fast manner, or some may be slower because of some other reasons. So we are marking it as a slow axis and fast axis. When the orientation or electric field orientation pulses go through the fast axis, it will be received faster, and once it is propagated through the slow axis, so its reception will be slower. So at the output side of the fiber, you can see that pulses will be reaching the output side at different times. So it is drawn that the input pulse are received at different times, that is it is marked as a fast axis pulse and slow axis pulse. So instead of one pulse we are receiving two pulses, right? And also the third figure shows that third figure is also elaborating the same concept, and in that case input pulse is shown, and it shows that the input pulses are two orthogonal pulses. One represents the electric field and other represents the magnetic field, and two orthogonal pulses are there. If it is going through the fiber. Fiber is also marked there and it is going through the fiber. You can see that at the receiver end, one pulse will be moving faster and other is moving slower, so that there is a time difference between these two polarizations of the input pulse. So it represents the time delay and this represents the polarization mode dispersion. This is the figure that represents the polarization mode. So that means two orthogonal pulses will be received at different times. So that means there is a time delay between these two pulses. So this is the basic concept. Before that we can explain it. You can see that due to fiber birefringence in the polarization state of an optical signal, it will result into broadening of the pulse, and the intrinsic factors such as geometric irregularities of the fiber core or internal stress, these causes the fiber birefringence. Also bending, twisting or pinching of the fiber causes the birefringence, and this in turn causes the changes in the polarization state of the optical signal. That means there will be changes in the refractive index of various modes. So if the polarization state varies with the distance traveled by the light through the fiber, and the fiber is birefringent, it causes each polarization mode to travel at a slightly different velocity, and that we have discussed with the help of a diagram, and the resulting difference in propagation times between the two orthogonal polarizing modes will result in pulse broadening, and this is the polarization mode dispersion. That means at the receiver side there will be difference in the propagation times between the two orthogonal polarizing modes. You can see it in the diagram. The two orthogonal polarizing pulses or modes are received at different times. Okay. The third diagram, so this represents the polarization mode dispersion. And the arrival time difference between the two orthogonal polarizations is given by delta T polarization is equal to L by Vgx minus L by Vgy, where Vgx is the velocity of the orthogonal pulse in the x direction and Vgy is the group velocity of the pulse that is traveling in the y direction. L is the length of the fiber. And this is the basic concept behind the polarization mode dispersion, and we can see that it will change with the polarization mode dispersion will change with the distance traveled by the light, and so PMD changes randomly along the fiber, and this can be a limiting factor in the long haul fiber optic communication system operating at high bit rates. So due to polarization mode dispersion, fiber broadening input pulse will be received at the receiver side as a broadened pulse. Pulse broadening will occur at the output side. So it is also a limiting factor in the case of long haul communication. And next is a problem, and that is the problem that is asked in the university examination question, and the question is that determine the normalized frequency at 820 nanometer for a step indexed fiber having core radius of 30 micrometer and a refractive index n1 equal to 1.480 and n2 equal to 1.46. Calculate the number of modes propagating in the fiber at 820 nanometer and 1300 nanometer and 1550 nanometer. That is the question. You are asked to find out the normalized frequency at 820 nanometer for a step indexed fiber. That is the first question. So first of all, you should remember the equation for normalized frequency. You know that normalized frequency is also called V number, and it has an equation V number or normalized frequency is equal to V equal to 2 pi a by lambda into square root n1 square minus n2 square. That is the equation. So you can directly substitute the values. You are given n1 as 1.480 and n2 as 1.46, and the lambda is also given. You are asked to find the normalized frequency at 820 nanometer. So you can substitute for lambda as 820 nanometer, and its radius is given as 30 micrometer, that is A equal to 30 micrometer. Simply substitute all these values and you will get a normalized frequency equal to 55.74. That is first question. And also you are asked to find out calculate the number of modes propagating in the fiber at 820 nanometer. That means at 820 nanometer, what will be the number of modes? You have the equation for number of modes, that is connecting with the V number as a number of modes m is equal to V square divided by 2. So you can substitute the value of V as 55.74. So you will get the number of modes m equal to V square by 2, where V square equal to 55.74 whole square divided by 2, that is equal to 1553 modes. That means 1553 modes will be propagating through the fiber at a normalized frequency of 820 nanometer. And a second question is that you have to find out the number of modes propagating through the fiber at 1300 nanometer and 1550 nanometer. That means at lambda 1300 what will be the number of modes, and also you have to find out at lambda equal to 1550 nanometer what will be the number of modes. So the same procedure will repeat for the next two cases, that is at lambda equal to 1300 nanometer, that is lambda at 1300 nanometer, V number is equal to 2 pi a by lambda into square root n1 square minus n2 square. N1 and n2 are the same as before and a is also same, but only the difference is for lambda. So you will get V as 35.15, and number of modes can be found out by the equation m is equal to V square by 2. So you can substitute the value of V and you will get m as 618, approximately 618, okay. And next you have to find out the m number of modes at 1550 nanometer, that is V is equal to 2 pi a by lambda into square root n1 square minus n2 square. Here only the difference is for lambda. Lambda is equal to 1550 nanometer, and you can substitute the values and you will get m is equal to V square by 2. So you will get 435. That means at 1550 nanometer the number of modes through the fiber is 435 modes, and at 2300 nanometer number of modes will be equal to 618 modes. That means you know that the three windows of operation of the optical fiber, that is locating at 900 nanometer range and 310 nanometer range and 1550 nanometer range, and at these ranges, operator ranges, the number of modes existing will be 1553 for the first case and 618 for the second case and 435 modes for the third case. So this is a problem that is asked in the university question, and this is simple substitution. You should by heart all the equations, then only you can do the problems. There are other equations to find out, there are other questions to find out a numerical aperture or acetance angle. You should by heart the equations that I have discussed in the previous sessions, and you can do problem directly by substitution. You can see that here root of n1 square minus n2 square. What is root of n1 square minus n2 square? That is numerical aperture, right? So we can write a V number as 2 pi a divided by lambda into numerical aperture. If once you are given the numerical aperture, you can find out the V number, okay. That's all about this section. In the next class we will go to the second module.